So we have looked at, first of all, what is focusing, if we go back several classes. And then we said, what's the surface that will give us good focusing? Since we can't get that surface very easily, we made an estimate of another surface and said, how well will that surface, the spherical surface, give us images? We looked at, when you have systems with several lenses in them, how do you analyze those systems? But finally, the point, and all of this we've talked a lot, the last matrix we looked at was an imaging matrix. So what does that mean? It means we're tracing rays, or we're talking about rays that start off from a point on the object, and all the rays from that point should reach one point in the image plane, right? Now, for many different reasons, all the points from one point on the object do not always go to the same point on the image. Okay? And that's why we have aberrations. Okay? So you can call aberrations as basically the deviations of the location of a ray from the perfect paraxial point, from the ideal paraxial point, paraxial image point. So we expect, if everything were perfect, the ray should have landed up in the image plane at a certain point, but instead of landing up at that point, it lands up at a different point, and that distance, that separation, or that error, is what we call an aberration. Okay. Now we classify aberrations because by doing so, it makes it easy for us to understand how to correct them. We will not accept, we don't say, okay, we're using a spherical lens, too bad, we're going to have to live with aberrations. We say, yes, there are aberrations. Now, how can I correct for them? What are the different things we can do to correct for them? So classification, one need to do that then is to understand these kind of rays, or under these circumstances you see these aberrations, and doing certain things is going to correct them. Okay. So the two broad classification of aberrations is, you have chromatic aberrations and monochromatic aberrations. Why do these come about? Why do they come about? Obviously, chromatic is to do with wavelength. Why do you have chromatic aberrations? Think of your imaging equation. The wavelength depends on refractive index, and every imaging equation that we have looked at, every matrix that we have looked at, obviously has refractive index in it. So the moment you send a different wavelength through the matrix itself is different for every wavelength, because it is a function of the refractive indices. So while you may arrive at a ABCD matrix for a system, actually, though I never said it before, the very fact I said n or n dash, it meant we were doing it for one wavelength. We were arriving and calculating it for a particular wavelength, right? So the perfect image position for an optical system is different for every wavelength. It's not the same. So the moment I send a number of different wavelengths through the same system, it's possible that if the separation in those perfect imaging positions is very large, you're going to see that, and then you clearly have a very large chromatic aberration. So we deal with these two differently, because one, even if your system is perfect, just the fact that different wavelengths are going through is going to cause aberration. So those are the chromatic, and those are the ones we'll deal with later. What we're going to deal with first are the monochromatic aberrations. Now, there are many different ways at looking at an aberration. I told you that we talk about the aberration as basically that displacement of the ray from its ideal position. But how do I quantify that? It turns out there are several ways of quantifying that. You could think I could quantify it in terms of an angular deviation. I could quantify it in terms of a transverse. So in this plane, the ray should have been here. Well, in this case, the ray should have been here, but instead the ray is here. So this is a longitudinal error, right? So I can measure it as a length, but as a longitudinal along the optical axis. On the other hand, I could continue this ray to this point and say it should have been here, but instead it's here. This is now a transverse or a lateral error. So I could use units of length to quantify the error, but even there it could be a longitudinal or a transverse length that I measure. It could be that the angle with respect to the optical axis is this, but now the ray is coming to a different point, so its angle is different, so I could use an angular representation. So I can quantify it in many different ways. And in fact, if you look at Oslo, you'll find it quantifies, it will give you the numbers in all these different ways. Okay. While we are doing ray optics, it is also very useful to look at the wave picture. Right? So I could also quantify it in terms of the wave error. Now, what do I mean by the wave error? If I had a perfect imaging wave, it should be spherical in nature. The wavefront should be spherical. But because it has an aberration, it's not spherical. So here in this image, you see, they have taken this reference spherical wave, but the actual wavefront has a different shape. It's this wave, right? And I could then quantify the error as the deviation between these two, between the perfect reference spherical wavefront and the actual wavefront. And Oslo will also give you the wavefronts. Why is it that a useful way of looking at the error? You can very easily picture how the wavefront looks, and that gives you immediately an idea of the kind of effect you're going to see in your image. Okay, so these are all different ways of quantifying or studying the aberrations in the system. Okay, so we'll start with the monochromatic aberrations. They were studied quite extensively and codified by this person Sagittal. So they are also often called the Sagittal aberrations. And there are 5 aberrations: spherical, coma, astigmatism, and then field curvature and distortion. Now I've written them in different colors because while they all affect the final image, these 3 actually they deteriorate the image. That means you don't get a good quality focus or a good focused image. Even if you do, you will not get a focused image throughout the image plane. There may be regions of the image that are focused, but there will be other regions that are not focused well. Okay, so they actually deteriorate the quality of the image. These 2, on the other hand, field curvature and distortion, they do not deteriorate the image. You always have a focused image, but you can think of it as maybe the image is stretched, or so it's focused, but it doesn't retain the same scales and ratios with respect to the object. Okay, so it kind of just deforms the image. And we look at these one by one. Now, in order to look at them, we need to make some definitions, right? Because again, we said we call an aberration, or we quantify an aberration as saying where the ray, how much the ray deviates from the ideal position. Now, what are the parameters I'm going to use to decide those things? So, in this figure, we are taking, and to make it simple, we are looking at circularly symmetric. So, our assumption here is we are dealing with circularly symmetric optics. Okay. One of the reasons for doing that, or taking that assumption, is I can always rotate. So I have an object here, you can say an object of height h. I can always rotate the object such that that height of interest to me lies along the y-axis of the system. And because it's circularly symmetric, it doesn't matter, right? So that helps in our analysis. So the parameters of interest are the image point in the paraxial image plane, that's what's shown here. And we want to find out where that ray that is coming from the object hits the image plane. In other words, what is the x and y coordinate of the ray as it hits the plane, the image plane? And this x and y are functions of the coordinates of the ray starting from the object and traveling through the optical system. So what are the coordinates there? Well, one is, this is the function of h, which is nothing but the object height, and r and theta, where the ray crosses the optical system. Now, of course, I want to be able to arrive at some equation like this, but it is not possible to arrive at an equation like this for any system. Maybe for a very simple system, you could actually work out equation that will tell you what is the x position of a ray, what is the y position of a ray. But you can imagine for any slightly complicated system with more than 2-3 surfaces, you're not going to be able to arrive at an equation very easily. So what Sagittal did was to use some ideas and the fact that we're using symmetric systems to arrive at general form of equations. We're not doing those derivations in this class. So the equations that are listed here, these are just the general form of the aberration equations. And you can see that you have one equation for the location of the ray in the x-axis according to the x location, and one for the y location. Now, they're very similar equations. They have a set of coefficients a, b, and I haven't written higher order terms, but they do have higher order terms as well. And you will notice that the a terms they are just a function of, or they are coefficients of just r and theta, some trigonometric form of theta, whereas, or of h. The b terms, if you notice, this is order 3, this is order 3, this is 2, but this is 1, so this is again order 3, right? This is 1, this is 2, so this is again order 3. So the b terms give you all the third order aberrations. And in fact, I can write 5th order, 7th order, and so on. You do not have the even orders here because of the circular symmetry. Okay. You could change this equation if you tilted your optical system or your lens and introduced asymmetry into the system. But because you've taken symmetric, the even orders disappear. Okay. So don't worry too much about these equations. The idea I want for you to get is, how do we quantify aberrations? And we're going to quantify aberrations by saying, I expected the ray to arrive at the perfect paraxial image point. It didn't. It landed up somewhere else in this plane, the paraxial image plane, and the coordinates of that point are x and y, and they are related in general to h, r, and theta h being the object height, r and theta being the point on where the plane, the entrance pupil of my optical system. And in terms of these parameters, I am able to arrive at a general form of what I expect the aberration equations to be. Okay? So I just want you to have that idea in mind. You can derive for a very simple system. You can't, you would derive them, you could derive them using some form of matrix optics, but it would get very cumbersome if you are doing it for a complicated system. So here he has derived it taking, so you take some things that you know into account. For example, you will know that any point, axial object point, will also lie in the axis and the image space. You know that any point, so any ray coming from an axial object point and traveling through any, so let's say I take a ray from here and it travels through any region, it's very bad, right? Travels through any region in one annulus. This is circularly symmetric. So any ray that goes either to this part of the lens or the same annulus but a different part of the lens, all those rays you know will image at the same point because it's symmetric. That must be the case. So you take these symmetry rules into account and you can trace ray through it and get it in terms of this. But it very quickly becomes complicated if you're trying to do it for more systems with many surfaces. Okay, so this is just to give you an idea that the x coordinate is going to depend, it depends on RH theta, but you can break up that dependence into a part that is dependent on just the A terms all have to do with just paraxial imaging. In fact, A1 turns out to be the transverse magnification, B1 is the spherical aberration, B2 is I think coma, B3 is astigmatism. And so you're saying it deviates from here so much because of coma, deviates so much because of astigmatism. So taking all those ideas, you arrive at this. Okay. Now, again, I need to be specific about the types of rays that are going to go through this system. So, let's revisit our definition of the meridional ray. We said it's the ray that lies in the YZ plane, and maybe this figure makes it a little easier for you to understand. We are now saying it is, in addition, it's the same thing, but to make it easier to picture, we're saying think of it as the rays that have angle theta as either 0 or pi. Okay, in the terms that we have given over here. You could alternately look at what we call the sagittal rays that lie in a plane perpendicular to the meridional plane, and that means those rays will have theta equal to pi by 2 or 3 pi by 2. Okay, why do we break it up into these kinds? Because it turns out meridional rays will contribute to certain kinds of aberrations, sagittal rays to other kinds of aberrations. Theta is the angle from the y-axis here. So take one, so if, maybe it's easier if I draw, this is my lens, okay, and I'm drawing an ellipse because I'm showing it to you at a tilted thing. This is the optical axis, and you have a ray that starts off, let's say, from an axial object point, and that ray happens to go here. Now, because it has gone there, what is its coordinates? This is the entrance pupil of our system. In this case, if you consider it to be a single thin lens, it's entrance pupil, exit pupil, aperture stop. What are the coordinates here? Well, its angle from the y-axis is this is theta, and its distance from the origin or the optical axis, this is r. And h is 0 because we have taken an on-axis point. Okay. So this tells us what is the coordinates of that ray as it enters the entrance pupil of the system. You can think about it like this. We are saying every ray that comes through the system, we would like it to go to the paraxial image point. But some rays make it to that point and some rays don't. And our contention, and what you're going to see is that why do some rays make it to the image point and others don't? Well, it depends on how they enter the system, where they enter the system. If they enter the system with R0, theta 0, H0, they're all going to make it to the paraxial image point. They're perfect paraxial rays. The moment the ray starts moving away from the paraxial ray, we know that they're going to have aberrations. And we're saying, this is saying that the amount of the aberration is going to be related to where they entered the optical system. In other words, what was the value of R and theta at the entrance pupil of the system? Okay. Is that clear? Okay. Okay, so his question is, because it's circularly symmetric, we can always rotate the system. So why bother about theta? You bother about theta because I can rotate the system when I'm dealing with a set of rays coming in one plane. But actually in an optical system, I have rays going out in all planes. So then when I'm analyzing all of those rays, I can't rotate it anymore. I could rotate it and get one set of rays to fall in the plane. But then I have rays that are in planes perpendicular to that, planes not perpendicular to that, and they all will be affected by the optical system differently. It's not just R, theta, H that affect the image, or you can think of it, it's not those terms directly. It shouldn't be surprising if you think about it. When a ray travels through an optical system, if the ray sees symmetry, you expect that the ray will behave in a certain way. But if the ray sees asymmetry, or a set of rays see asymmetry, it shouldn't be that surprising that they behave in a different way. And depending on their R, theta, H, they're either going to see the optical system as symmetric or not. We are using a symmetric system. It has an axis of rotation. But if a ray comes from an off-axis point, one ray hits the top of the lens, one ray hits the bottom, those two rays are seeing completely different, they see the optical system in a different way. Right? So the way the ray comes into the system can introduce asymmetry and does introduce asymmetry, and that causes one set of aberrations. Okay, it will become clearer as we do the definitions. So just to get these concepts clear, again, we said meridional rays, YZ plane, and here we have a set of rays coming from one object point, and these all lie in the YZ plane. They all have the same value of theta, but they all have different R values. Okay, and we define a sagittal plane. The sagittal plane is what is in this, I don't know if you call it pink. It's in a plane perpendicular to the meridional ray, meridional plane. So you have the optical axis here, you have the lens, and then you have this sagittal plane perpendicular. Now below, I'm showing you what I was just talking about. In this case, you can consider that this is your lens, this is your object, and you're looking at the rays coming from this point, the extreme point of the object. Now you can see that the rays coming from this extreme point, they're all coming from the same object point, but this ray lands up at a certain angle on the optical system, and this ray lands up at a different angle on the optical system, and that's what's shown over here. Here they're not coming from a point, they're coming from infinity, so you have a parallel set of rays, but you can see that the way they are incident on your optical system is different. They bend differently here to form an image point here. right? These are all rays in the meridional plane. From that same point here, if I now drew the rays coming to the lens, it's hard to draw this, but I'll try. Okay, let's say I'm now drawing what's happening in the plane perpendicular. And so these rays are going out sidewards. So this is a side view, and this is now a top view. I'm looking down at the system from here and looking at the sagittal rays. So they're coming and hitting the lens from the side and getting bent. They're hitting the lens at different points. This is the on-axis ray. This is the ray traveling along the optical axis. These are the rays coming to the side of the lens. They're all getting bent like this. But you can see they all see the lens in a symmetric way. So it shouldn't be surprising that this could cause some aberration, because these rays see the lens asymmetrically. So there's an asymmetry over here, whereas there's a symmetry over here. And in fact, the aberration astigmatism arises because of asymmetry that comes from the way a ray is incident on the lens. Okay. Yes, you're right. Your question is if in this case I had rays coming in like this or parallel to the optic axis. You're correct. In that case, I will not see the asymmetry and the error would be different. Yeah. Then that is identical to this case actually. Right. So you have some aberrations which occur only for off-axis. So in fact, I broke up the aberrations into monochromatic and chromatic, but in monochromatic, we will first look at the on-axis aberrations and then we'll look at the off-axis aberrations. You had another question? No. Okay. So the sagittal rays come, now you notice here the sagittal rays, even though they're coming from an off-axis point, they still see the system symmetrically, right? And that's why you see there is the difference in the final image depending on how the rays have traveled to the system. And to make it easier for us, we will say these are meridional rays, these are sagittal rays, and that immediately tells you, oh, they are seeing the system symmetrically or they are not. Right? You don't have to define those terms every time. Okay. Sagittal rays propagate in a plane perpendicular to the meridional plane, and it also contains the chief ray. Meridional ray plane also contains the chief ray. So that basically that intersection between these planes is where the chief ray is traveling. Okay. Yes, you're right. The chief ray is both a sagittal ray as well as a meridional ray. It is both of them. Yes, it satisfies the definition of both of them. Okay. Sagittal rays are skew rays except for the chief ray. Now, I mentioned skew rays some time back, but I'll refresh your memory. Skew rays are rays that crisscross the system. They don't go along the optical axis. They can avoid the optical axis completely, and I think I have a picture that will help you understand that a little better. So I have this is rays traveling within a fiber. So you're looking at the cross section of the fiber. These rays are all in different planes. It's not in one plane. So it's traveling like this, then traveling like this. But you can see they never travel along the axis. These are skew rays. Okay. So skew rays are not in the meridional plane. They do not cross the optical axis. They're definitely not parallel to the optical axis, except for the chief ray. Okay. Obey these different features. The chief ray happens to be a sagittal ray, and skew rays are also sagittal ray, but the chief ray does pass through the center of the aperture stop and is both meridional and sagittal, as we discussed. Okay. Now, since I want to quantify them, there are, again, you've seen those aberration curves in Oslo. There are several ways of quantifying. There are all these nice curves over there. And by convention, they do not give you the axis labels ever. They will just show you the curve and you must understand what curve it is and what is being plotted. So this is one case where the teacher will not jump up and down and say, you didn't label the axis. They don't label the axis. It's quite infuriating, but that's the way it is, right? But I might still ask you what the axes are to make sure I know that you understand what they are. So in that case, you'll have to tell me what they are. One way of plotting aberrations is to plot something called the ray intercept curve, and it is basically where the ray intercepts the paraxial image plane. But rather than plot it in terms of x and y, we plot it in terms of this axis is the tangent of the angle that ray makes. So let's say I have, this is my paraxial image plane, this is the optical axis, and I have a ray that hits the plane like this. Then this is u, and I'm plotting tan u over here, and this is the transverse error, and we're saying maybe, and it's negative, you can see, so this point would come over here. Okay? The standard way of plotting these curves is that you take the ray, so if this was my optical system, the ray that you plot on the rightmost of this ray intercept curve is the ray coming from here. So this is ray number 1, and that corresponds to this point. So the ray from the top of the lens, its transverse aberration is plotted against the tangent of the angle it makes with the optical axis on the rightmost part of this curve, and often we will just call these the RIC curves. So if I take another ray, let's say that ray started from this point and it went over here. This is the second ray. So it makes this angle, it has this transverse aberration, so maybe it comes over here. Okay? So you plot in this direction. It will get clearer as you see more of these curves and we plot more of them. Okay. Our goal is that we want to correct for the aberrations. We don't just want to observe them and quantify them and say, oh look, I have so much of spherical and I have so much of this. We want to quantify them and say, I have so much of this aberration, how do I correct it? Right? Now, can you think of some things we could do to correct? What can we do that we could correct it? What optical operations, or what could I do with my optical system to help correct? The lens can be made asymmetric. Okay, so I will rephrase that. I'll say maybe we can, I've given away an answer, maybe we can reshape the lens. You still have spherical lenses, but they don't all have to have the same shape, right? One of the answers came up, you can play around with the power of the various lenses in the system, right? What else? Okay, you can play around with the material. He said refractive index, so maybe play around with the material. Okay, what else? How do I change my optical system? So wavelength is not a way to change my optical system. Remember, the goal of correcting an aberration is you have designed an optical system, or you want to design an optical system that works for a certain wavelength or range of wavelengths and should have a certain power. Correcting for aberration does not mean you change your requirement. For your requirement, how do you get the least aberration? So even here, when I put power, I do not mean that you change the power that you required that is required of the optical system. I mean here that if you have multiple elements, you can change the relative power. So the overall power of the system is the same, But maybe you had lenses f1, f2, f3 and you change it to f1 dash, f2 dash, f3 dash such that the total power is the same. But because you've changed the individual powers, the way the ray bends is different and therefore an aberration is less. Okay? So correcting for an aberration is not changing your requirement. It is for your requirement, how do I get the best out of the system? Okay. So there are a number of things that you could do. When we said shape, I can take a convex lens, I could take a meniscus lens. Well, it doesn't look like that, but you get what I mean. You could take a concave lens, you could take a plano convex lens. You could have all the lenses with positive, at least. They could all have the same focal length, but the shape is different. You could change thicknesses within your system. So when I say thickness now, it does not mean just the thickness of this lens. You now understand it also means the distance between opticals. So I can play around with that. Glass type, material, that is refractive index, spacings, right? So I can change the thicknesses of the lens. These are related if I'm talking about thick lenses, okay? And I thought you would all tell me this because we talked about this a lot over the last few weeks. You can change stop location. Okay, so I think we won't start on spherical aberration because I don't have enough time. But what we will do in tomorrow's class is start looking at these specific monochromatic aberrations in detail, so that in the lab tomorrow you're going to look at an optical system, look at its aberrations, and from tomorrow those other crazy curves in Oslo ought to make more sense to you. And then your goal will be, how do you reduce the aberrations of the system? Okay, so today's class, I started with the continuation of the matrix optics, and we took the system that we had developed that converted the ABCD matrix of any optical system to that similar to of a thin lens, and therefore helped us with our analysis. And we then took that equation today and pushed it further and arrived at the imaging condition for any optical system, right? After that, we started looking at the aberrations. First of all, and in order to do so, we haven't really got to the aberrations, but we spent most of the class saying, well, if I want to quantify the aberrations, how do I quantify them? What are the parameters and terms I'll use to quantify them? And then we looked at, well, I want to correct them. What are the variables? What are the tools that I have available to me to help correct the aberrations? Okay. So from tomorrow's class, we will look at the specific monochromatic aberrations. Okay. Thank you.